In this video, I'm going to be showing you about linear momentum and impulse. So the very first thing to start with is linear momentum. Now I mean linear because there's different types of momentum. We can have things like linear momentum, but we also have things like angular momentum. There's all sorts of different kinds. But I'm going to start with just linear momentum. Now linear implies just a straight line. And we have an equation first of all that can actually help us to define things. So it goes like this. P equals mv, where P is the momentum. So this here's the main equation we need. Okay, so that right there, that's the momentum. We'll be able to figure out the units in a second. We have m, of course, is the mass, and that's measured in kilograms. Then we have v. Whoops, that's a bad k there. There we go. So v, that's just the velocity. And that velocity is measured in meters per second. So there we go. So what's the momentum measured in then? It doesn't have its own special units, but if you just know how it's defined here, so we have mass, well that's units of kilograms, and we have velocity, which has units of meters per second. So momentum then must be measured in kilograms, because that's these things, times meters per second. So that's the units for linear momentum. Now, like I said, momentum is a vector, which means you normally have to say what direction it is. And we can have different units as well. I'm going to show you an alternate unit in just a second here. So it turns out we can also say, or we can say Newton seconds as well. There's lots of different ways of saying it, but these are the main ones. Now, when is it used? So what do we use linear momentum for? Well, it's often used to tell us about things like collisions or even explosions or things like that. So it's useful for telling us about collisions and explosions. Not just those, of course, but it's especially, at least in physics classes, used for collisions. So that means two things run into each other. So maybe we have, one thing comes in like this, another thing comes in like this. So this is some object and some other object. And when they meet, what happens to them? Well, it all depends if they stick or if they bounce or if they sort of half stick and half bounce. But basically, we can use momentum. It turns out we can use what's called conservation of momentum in order to help us to predict where different things will go. So if we know that, let's say this object and this object run into each other and they bounce, and if I know the direction and velocity, if I know the direction and speed of one of the objects afterwards, it turns out I can work out what the other one does. So this can help us a lot in collisions. So that's linear momentum. Now there's another thing though that we can use, and it's actually very closely related, and it's called impulse. Now the impulse, it has a letter I to denote it here. Now the impulse, it can be defined a few different ways. One of the ways is just by calling it F delta t. That tells us something about the force and a change in time. But we also have a version that goes m delta v. So this is the equation or equations for impulse. So I equals impulse. We'll define the units in a second here. So we have F. Oh, by the way, impulse is a vector, force is a vector, and velocity is a vector. Should be careful here. So F, well that of course equals the force. And that force is measured in newtons. Now we have delta t. That's just some sort of time or a change in time or a difference in time. And that's going to be seconds. M of course is mass. And v is, of course, velocity. So that's the same thing as we had here. So we have mass and velocity like we had before, except this time it's mass times change in velocity. So I guess we'll say that. So delta v, that's equal to change in velocity. So that tells us, starts off at a certain speed, finishes at another speed. Remember, the word velocity just implies a direction. So that's that. Now how can we then define impulse? Well, impulse will then have units of, well let's see here. Maybe I'll actually be able to just pick it up and move it. I think I need a bit more space. Whoops. Didn't mean to do that. I would actually like to pick up all of this Oh, it's not going to let me. Isn't that nice? That's fine. So if I look at this then, I can do the units for impulse. It's going to be, well, units of F, which is newtons, times units of delta T, which is seconds. Or I could also say units of M, which is kilograms, times delta V, which is units of meters per second. Now look very carefully at these units, kilogram meters per second. Look back at this one here, where we had momentum was in kilogram meters per second. And remember I said it's going to be or Newton seconds. And the reason why is right here. Turns out impulse and momentum are very closely related because impulse is nothing but a change in momentum. So sometimes I like to rewrite this as I equals delta P. In other words, the impulse equals a change in momentum. That's, I think, a really nice way to look at it here. So we could say that the impulse is a change in momentum. So of course it has units of momentum. I mean, it makes sense then. If impulse is a change in momentum, see, that's m delta v. If we just had mv, that would be just momentum. But we have m delta v. That implies a change in something. Now, the mass doesn't change, we're assuming, so that's why we say delta v here. And of course, F delta t, well, that's something useful for us. But there's a few extra little points I'd like to point out. Sorry for the pun there. But we have this. If we have I equals F delta t, I want to show you something. I want to show you a graph. So what if we have a graph of a force over time? So of course this force would be in newtons and this time would be in seconds. Well, it turns out if you have some sort of collision happening or some sort of thing going on, so maybe, I don't know, maybe we have some force that goes, straight across, all of a sudden it goes down, all of a sudden it goes across again. So let's say this means you apply a force here, and after a certain time you apply less force, and then you apply that same different but lesser force here. If that was the case, it turns out you can figure out the impulse and therefore the change in momentum in something by looking at this graph. Now what I like to do is when I look at a graph, a key feature that I like to teach students is that, well, there's only basically three main things we tend to do with graphs, at least in high school level physics and even math. One thing we can do is tell the y-intercept. That's sometimes useful. Another thing we can do with a graph is find the slope or the gradient. Remember, that would be just, picking a point and picking another point and finding the rise over run. In other words, the delta y over delta x for that thing. And if I did a slope, look at the units carefully. I would do units of these things over these things. In other words, I'd have f over t. And take a look at this, f over t. No, that's not this. Another thing I can do, however, is take the area under a curve. And if I do that, if you remember how to take the area, let's say I wanted the area under this curve from, I don't know, here to here, let's just say. Let's just say I wanted that area right here. If I wanted that area, that would be units of, well, length times width, or, height times length. It depends how you want to define it, but it's basically these things times these things. In other words, I'd have things with F times things with T. Do you notice that's like F times T? So what this tells you is this, that the impulse, remember, therefore, the change in momentum is equal to the area under a force versus time graph. So that's something really useful, because then you can have some sort of collision or some sort of thing happening and you can figure out the impulse. So now, how is this actually useful? This is actually very, very useful. It helps us for a lot of things. So actually, I'm just going to continue on here. So impulse. So it's useful for, well, let's see here. We can say forces applied over a certain time. You see, if we have a force that's being applied in some given time, then we can actually use this really well. It can use things like, oh, I don't know. We can actually use it in rock climbing. It turns out if we're going rock climbing, This is just a use that I have, at least. So I've got, let's say if I'm out climbing with my friends here. So let's just say I'm out there and I'm climbing. And so here's me, and I've just fallen. So thankfully I have my rope with me. So here's me, and I'm tied to some sort of rope above me here. Now I'm falling down. Okay, so my velocity is going downwards. Well, I want my rope to basically stop me from falling. So if you look at this, we have the impulse is equal to F delta T, which is also equal to M delta V. So what I can do then is, if I'm in the middle of falling, there's a reason why I want a certain type of rope. I'm going to show you that actually. So if you're climbing, you can get what's called a static rope, or you can get a dynamic rope. Now the rope that I want to use to stop me from falling, I want what's called a dynamic rope. And that's because, well, actually I'll explain that. So right here, what I want to do is I want to look at the force that's going to be applied onto me, but also onto the rope. Because you see, if there's too much force on the rope, it'll either break the rope or it will break my back. And neither of them is wanted. So I want to minimize this force. So what if I just solve for this force? I say F, and I want to get the force by itself. Turns out I'm going to ignore the impulse, even though I'm using the equation for it, but I'm going to use F delta T equals M delta V. If I want to get F by itself, then I have to divide by delta T, so I could say it's going to be M delta V over delta T. There's the vector parts here. That means smaller delta T leads to larger force, just like a smaller, just like a larger delta T leads to a smaller force. Now this is what I want. I want to reduce the force. So it turns out if I make the delta T bigger, if I make the time larger here, dividing something by a larger number means this is smaller. You can always try it, right? Divide by 5 or divide by 6 or divide by 7 or divide by 8. And you'll see that this value right here actually becomes smaller as you get larger values of time. Well, that's exactly why we want what's called a dynamic rope. See, what we want here, in a rope at least, we want this. We want to have a larger delta T. In other words, we want the time that we apply the force onto the rope, we want it to be a larger time. So having a stretchy rope, that will help, because if the rope stretches a little bit, then you apply the force over a larger time, and that means then that you end up with a smaller force. So that's really nice. That's why, at least in rock climbing, this is really useful. I mean, just other uses that I like to think about, well, rocket engines. It turns out that if you have a rocket engine, it's all about applying a force over a time. In fact, we have a word that we call specific impulse. That's actually a very common word. Almost anybody who's in rocket design will actually know. So if you're a rocket scientist, you know lots about specific impulse. And that tells you what kind of force per unit time that some sort of engine can give off. Turns out the word specific means something special. But I mean, we have these words called specific impulse. There's even things called, impulse drives, not only in science fiction, but it turns out in science fact, we have things like ion impulse drives. So some of that stuff sounds really neat, but impulse is very useful, not only for collisions, but also for rock climbing, rocket engines, whatever else. So I'm going to give you an example here. So I thought, well, okay, I kick a ball, and the mass is 0.5 kilograms, and the ball is initially at rest. Now, how fast will it be going after I've kicked it? Okay, so here's me, and I'm just kicking the ball, right? I mean, there's nothing really that complicated going on. I basically kick the ball. So the ball just, initially it's at rest, and finally it's got some movement. So it has the following force versus time graph. So you're given that the force applied onto the ball over a given time, well, you can see at time t equals 0 seconds, there's no force being given to it. All of a sudden here, I start to apply a force here. This is the act of me kicking it. So my actual kicking only lasted this long. So kick lasted, well, how long is this? Let's see, the kick lasted, well, from 0.1 to 0.3. That's, 0.3 minus 0.1 is 0.2. So I've got, my kick lasted only 0.2 seconds. During that time, I applied a force of, well, some force, a larger force, up until a maximum force of 20 newtons. Okay, so that was my maximum force here. The maximum that I gave it was 20 newtons, although I did give it less, right? I mean, I started off by giving it, well, 0.01 newtons, 0.02, all the way up to, 10 newtons, then all the way up to 15, all the way up to 20, and then back down. This is somewhat more realistic, at least, because you apply a force over a given time. Now, it doesn't have to be straight lines. It can be curves. It can be whatever. But if I want to know how fast it will be going, I could probably use this equation for impulse. And it says that impulse is F delta t equals m delta v. I'm just writing it again. So if that's the case, well, the impulse necessarily, it isn't necessarily important to find this impulse here. But let's look at what we can do with this graph. And I alluded to this before, saying that, well, if we look at this graph, we can only do three things with it, really. Well, we can do lots more than that, but we could find a y-intercept, we could find a slope, or we could find the area underneath it. Which one is useful? Well, the area underneath this one is the only one that's useful because I want to do these things times these things, because the area of something is length times a width. So in this case, I've got F times delta t, so the area will equal F delta t. This is going to be important. You see, from this graph, I can tell the area of this. See, I can find this area right here. Now, what's that area? Let's see. This area is going to be, well, height times the width divided by 2, because the area of a triangle is equal to just base times height divided by 2. That's sort of a nice, easy way to remember things. For triangles, at least, the area of a triangle is the base times the height divided by 2. So the base here, in this case, then the area is going to equal, well, the base is 0.2 seconds wide, and the height is 20 newtons. And if I multiply those, well, 0.2 times 20, we could actually figure that out. But actually, I don't want to just stop there. I want to say this, that the area equals F delta t, but look carefully, it also equals m delta v. So I just want to keep going. So the area is F delta t, which is m delta v. Therefore, the area is, well, the area is this right here, which that right there equals, then I have my m delta v here. I don't know if that makes any sense. I'm just filling it out. So I've got my force times my change in time. Of course, I had to divide that by 2, didn't I? That was really important here. So then my area is the base times the height divided by 2. Now, what if I just wanted to figure out this value right here? What is this? I don't need a calculator for it. Turns out I can do 20 divided by 2. That's just going to be 10. And 10 times 0.2 is just 2. So that means I know that F delta t equals 2. And I was a little bit sloppy with my units here. These had units of seconds. These had units of newtons. So it's 2 Newton seconds. So that's useful, but I'm not done yet. Remember, though, I can set that equal to m delta v. So that means I know then that 2 equals m delta v. And if I want delta v, then delta v is just going to be 2 divided by my mass. So if I have this right here, well, I have 2 divided by, and what's the mass of the ball? It's 0.5. So then I can say, well, 2 divided by 0.5, that's just going to be 4. That's going to be 4 meters per second. So that's my change in velocity. So if I had a certain starting velocity, well, I would know that my final velocity is 4 meters per second more than I started with. Okay, that's how it is in general here. That's my change in velocity here. However, what I can say then is, well, I was a little bit sloppy here again, because what I should have done is told you the direction that I traveled, but that's okay. We can say it's 4 meters per second. I did ask how fast is it going. I didn't say what is its velocity. To know velocity, I would need to know the direction. So I could have said, I kick it east. Well, then this would be east. But keep in mind, because my initial speed was 0, because it was initially at rest, well, 0 plus 4 meters per second is still 4 meters per second. Or I could say, in other words, 4 meters per second minus 0. That's how we do a change in something. We do the end minus the first. And if that's the case, then this is the speed of the ball. So it initially was going 0 meters per second. It was initially at rest. That's the key thing here. And finally, it's going 4 meters per second. So that's how we can at least use something that may look really complicated and with a weirdo looking graph, and we can use our nice equation for impulse. It turns out this right here is also the change in momentum. So I could have been asked that. I could have been asked, what's the change in momentum on the ball? Well, that would be the same idea as just find m delta v. But if I wanted m delta v, it's the same thing as f delta t. In other words, see this this f delta t here, this 2 Newton seconds? That's the change in momentum. So if I was asked for the change in momentum of this ball, I would say, oh, it's simply 2 Newton seconds. But I wanted to go a little bit further. I wanted to know how fast is it going at the end. So we had to use this 2 Newton seconds to actually work forward and figure out that it was 4 meters per second. So that's how we can deal with some basic definitions about momentum and some specifics with impulse.